In this video, I will show you how to use the expression that we have in an RL circuit the moment you close the switch. So what I have here, let's make a switch. What I have here is an RL circuit, and the reason why this is an RL circuit is because it includes a resistance, the resistor R, and the inductor that we use the symbol L. I also have a battery here, and I do have a switch, and I close the switch the moment t equals 0. Now, if the inductor was not part of the circuit, then I would really have simply one resistor and the battery, and I know if I apply the loop rule, I'm gonna get that the current in that case would be EMF over R. Okay, so this is if I did not have the inductor present in the circuit. The current would be just completely constant, always equal to EMF over R. Now, this is how you can find I naught in your expression. So the current as a function of time in an RL circuit includes I naught, which is the maximum current that goes through the resistor. That maximum current, you can find that maximum current by simply saying, well, if the inductor was not there, then I would get EMF over R for the current in the resistor, okay? And this is what I'm gonna plug in here. Now, this symbol, this is the Greek letter tau, and this is equal to L over R. Let's say, just for the purpose of doing the calculations, let's say we have an inductance of 20 Henry and we have a resistance, let's make it simple, we got 2 ohms, so this will be 10 seconds. Okay, the units of the time constant are the time units, so it will be seconds. Now, for the purpose of doing the calculation, let's say we have 2 batteries of 1.5 volts, so this would be 3 volts. As I said, we have a resistance of 2, so the maximum current will be 1.5 amperes. Now, the expression that we have then becomes 1.5 times 1 minus E to the minus time divided by 10. Okay, and this is an expression that only that depends now only on time. If you give me a time, I can do the calculations and tell you what the value of the current is. Now, it is important to have a qualitative understanding of what this means, what this mathematical expression means. As soon as I close the switch, the inductor will oppose what the change that I'm making. What change am I making? When I close the switch, I want to change the current from 0 to EMF over R. The purpose of the inductor is to oppose that change. And if you actually if you make an RL circuit and you measure the current, the moment I close the switch, the current should be at EMF over R. Okay, the current should be here at EMF over R. The moment I close the switch in an RL circuit, the current is nowhere near EMF over R. The moment I close the switch, actually, the current is exactly 0. Okay, the inductor at t equals 0 is doing a great job in opposing the change that I want to make. However, the inductor will not be able to keep opposing that change. The current will slowly increase until, slowly it reaches the value of EMF over R. Now, it approaches, it's important to know that the current really becomes EMF over R when t goes to infinity. So in theory, you have to wait an infinitely long time for the current to become exactly EMF over R. However, if you wait, say if this is 1 time constant, 2 time 2 time constants, 3 time constants. If you wait 3 time constants, so in this case, if I wait 20-30 seconds, my current will not be exactly EMF over R, but it will be somewhat close to that value, to the value of EMF over R. So this is what the graph of the current versus time look like for this. And if you say, okay, let's say I do wait for 10 seconds. So what is the current when t equals 10 seconds? Then it will be 1.5. 1 minus e, so this will be 1 to the minus 1, and this will give me a 0.95 amperes. Okay, so if you wait for 1 time constant, you're roughly 2/3 of the maximum current that you will have. So right here, this is about 2/3 of the EMF over R.